Yeah. Okay, test. Actually, maybe I should put it on this. I don't know. I'm gonna turn this way. I'll have to turn my whole.
Just that for the
Yep.
person. Zoom people, can you hear us? If you cannot hear us, please let me know. Oh no.
Yes, they can hear.
Okay, good.
All right, and that's not showing over here.
I think it's good to start now.
Get started.
Yeah, people coming from. Okay. Yeah. Okay, thank you very much for gathering again. And let's have a second half of the Splinter session. At the first, we have invited talk by Dr. Rachel Osten from Space Telescope Science Institute and Johns Hopkins University about all the wavelengths. Yep.
All right, thanks everyone. I hope you had a good coffee break, got some sunshine, got some water, and let's get back to talking about this flare and eruption analogies. So I was asked to talk about the observation part. I do not discriminate. I observe across the electromagnetic spectrum, and so I'm going to tell you about all of the wavelengths. We don't have an infinite amount of time, so this talk does not have infinite spectral resolution. I'm going to have to do some very broad thinning to get through all of the wavelengths. And my slide is not advancing. Oh, here, there we go. Okay. So we heard a little bit already about modeling of flares and coronal mass ejections. These are inherently multi-wavelength. It involves flares and eruptive events involve pretty much all layers of the solar stellar atmosphere. There's a bunch of different physical processes to study, and that leads to basically, you can fine tune the wavelength regions that you want to observe depending on what questions you want to answer. And so there's really only two parts to this talk. For the first one is a very brief run through of some of the different physical processes, atmospheric layers, wavelength regions. This is going to be sort of an educational smorgasbord of things that you can learn, not necessarily from a multi-wavelength perspective, but taking each wavelength by itself. And then in the second part, I'm going to talk about different kinds of observing strategies that you could use for multi-wavelength investigations. And I thought it would be interesting to harken back to what might be the very first multi-wavelength stellar flare campaign. This was a paper in Nature in 1964. And Sir Bernard Lovell was able to get into Nature by observing a radio and an optical flare from EV LAC. I don't think that would necessarily cut it today for Nature. But just an interesting example that this actually goes back quite a long ways. So I'm going to start at low frequency, the low frequency radio end, work my way up to X-rays. There's a sort of common format for these slides that if I'm talking about something that has to do with flares, it's going to be in red. If I'm talking about something that has to do with eruptions, it's going to be in blue shift, get it? So when you're looking at low frequency radio wavelengths, you're generally looking at coherent emission. This has already been covered a little bit, especially on Monday's Splinter session with talking about magnetic fields in the stellar and substellar regime. But you basically are looking at plasma or cyclotron maser emission. This is an example of a study that was done by Jackie Villotson and Greg Hallinan with low frequency radio bursts on the very lower part. They also had high frequency observations. These are characterized by highly circularly polarized bursts. Because there is a very nice mapping between the plasma frequency and the electron density in the atmosphere, where you're seeing the phenomenon or the magnetic field strength in the atmosphere where the phenomenon is happening. And the cyclotron frequency, the observing frequency, gives you a very nice discriminator for some fundamental processes. In eruptions, we talk about low frequency radio waves. I'm pointing out here type 4 bursts. These are characterized by highly polarized emission associated with energetic particles. The example that I'm showing here is from Andrew Zick's work on Proxima Centauri, where they saw what they inferred to be evidence for type 4 bursts on the sun. We know that these are associated potentially with coronal mass ejections, sometimes with flare-associated electrons. And they said that this was highly suggestive of a CME, not conclusive, but highly suggestive. We also have type 2 bursts. This is an example of a solar type 2 burst dynamic spectrum. We're actually going to hear about the first potential detection of a type 2 burst on a star later on in this session. These type 2 bursts are formed when a shock that's formed by the coronal mass ejection is passing through the atmosphere of the star. We've already heard about this a little bit in the first part of this Splinter session. There's a very characteristic signal of the burst in frequency and time that enables you to diagnose the velocity with which the shock is traveling through the atmosphere. You commonly see this in the sun for fundamental and second harmonic emission, which you can see as the two distinct areas on that dynamic spectrum. Moving a little bit higher in wavelengths, we've got centimeter and millimeter waves. Here we tend to see gyrosynchrotron emission from accelerated particles. This is an example of long exponential decays in some of these flares. This one is an example from EV-LAC, which had a flare decay that lasted for many hours, even past the end of the observations. These types of observations tell you that you're looking at one, accelerated particles, and two, that they're well trapped in a magnetic loop. They're confined in the loop, they're bouncing around. Some of them will precipitate and then you will not see them anymore, but most of these are well trapped electrons. Okay. In the last couple of years, there's been some interesting results at shorter wavelengths, at millimeter wavelengths. Some at first serendipitously observed flares seen at millimeter wavelengths from a handful of M dwarfs. Meredith McGregor studied some archival ALMA observations of first Proxima and then AU-MIC, which is shown here, finding these very impulsive, very short duration flares that lasted for maybe a few seconds to a few tens of seconds. When you look at the spectral index, this is consistent with optically thin emission, and hence you can actually place some constraints on the index of the distribution of the accelerated particle population. This is likely gyrosynchrotron, maybe even synchrotron emission from accelerated particles, in contrast to the case where you have a very nice exponential decay, flare decay. The very short duration of these bursts likely indicates that they are particles that are precipitating from the magnetic trap. Okay, so that was flares. Let's turn to signatures of eruptions at radio wavelengths. This is a little more speculative on the stellar side, and what I'm actually showing is a case from a solar radio flare that observed what were called negative radio bursts. And so you can see here, I apologize, I don't think the people online can see my cursor, but the pre-flare emission is normalized to unity at the number of different frequencies from 1 to 8, 1 to 10 gigahertz. And you can see that there is a dip in the decay phase of the flare, which is a function of frequency. The interpretation here is that you're seeing absorption of the cool material that is part of the coronal mass ejection. You can model that, the expected behavior as a function of frequency at 2 different times, one of which corresponds to when a CME was observed in a coronagraph for these observations because they're solar observations. So you have all of the wavelengths that you want usually. But this is a very kind of speculative thing that we might be able to look for in stellar flares that could be another signpost for an eruption. So I just want to put that out there for the radio-minded folks in the audience. In the infrared, recently there was a paper by Ward Howard. I don't know if he is at this conference. I have not seen him yet. So he reported on some serendipitous flares observed on the TRAPPIST-1 stellar system. This star was being observed, of course, because of all of its interesting planets. But JWST is so sensitive. You can see these amazing infrared line and continuum measurements, which is fairly unusual, showing Passion and bracket beta for the first time. You can see the profiles of the flares at these different wavelengths. There was also some continuum emission, which fit with a black body, and you get a fairly low black body temperature of a few thousand Kelvin. So this is telling us about line and continuum emission from lower in the atmosphere of the star. If you happen to be looking at a star that has a dusty disk around it, you can also see that in the infrared, but I didn't have an example to show you. In the optical, there's been a huge amount of observations of optical flares, and I'm not going to do this justice because I had one slide. But here you see photospheric emission and chromospheric line and continuum emission. When you look at time-resolved spectroscopy of M-dwarf flares, you can see the evolution of the continuum emission. And what I'm showing on the right is a temporal sequence of low-resolution continuum observations from Adam Kowalski that starts at green and then goes to red. So you can see this is during the rise phase of the flare. The spectral shape, the spectral energy distribution is changing markedly to peak. And then in the bottom panel, you can see the evolution in the decay phase of the flare. So the top curve is right at the flare peak, and then through the decay phase of the flare, you can see that decay again. There's some very characteristic signatures here of a Balmer jump, an increase in the white light continuum. I'm not going to talk about what is interesting in there, but that can be maybe part of the discussion later. That's the continuum emission. We also see evidence for line broadening. We discussed this a little bit in the previous session in the context of evidence for eruptions, but you see these in just flares. This is an example from Yuta Notsu's paper showing some line broadening out to a few hundred kilometers per second, but very symmetric. And this figure has already been shown several times, so I don't need to go into it in a huge amount of detail, but this is an evidence, has been used as evidence for prominence eruptions, where you can see blue shifted chromospheric material as well as dimming in the decay phase of flares. And so again, you're looking at, this is chromosphere and photospheric emission, but you're looking at something getting in the way of the flare, and that is evidence, used as evidence for eruptions. Okay. Let's move to the ultraviolet. Here we're moving a little further up in the atmosphere. Again, line and continuum emission from the chromosphere, but now we're moving up into the transition region, even into the corona. There's a couple of coronal forbidden lines that show up in the UV. So this is a classic paper from Suzanne Hawley showing observations of flares on AD Leo. These are redshifts in UV lines, seen as signatures of chromospheric condensations as the material is going back down into the lower atmosphere. Okay. Again, in the ultraviolet, looking at continuum emission, these are two different papers looking at the far UV continuum and then in the near UV. Let's look at the one that's on the far left first. This was a flare observed on the M dwarf GJ674, where Cynthia Froning fit this as the continuum as a black body and found a temperature of about 40,000 Kelvin, which is extremely hot. And then in the near UV, this is a paper from Adam Kowalski using Hubble for the near UV and then combining that with optical observations and found enhanced NUV emission in this M dwarf. And you can see that there's actually two different components that are required to understand this. There's this black body emission, but then there's Balmer jump emission that gets reproduced by his radiative hydrodynamic models. Okay. Staying in the ultraviolet for just a second, there was an intriguing paper that Park Lloyd published a couple of years ago on an FUV flare in a young solar analog, Epsilon Eridani, seen in the ultraviolet in lines of silicon-4 in the black. And then I mentioned that there are some of these coronal forbidden lines. The time dependence of one of the coronal forbidden lines, iron 21, compared to iron 12, looks like it's showing some kind of dimming feature, but those are the only coronal signatures that you have access to, so you don't have the broader context of what's happening in the rest of the corona. So interesting, but still a little speculative. Let's go into the EUV and X-ray, and here you're seeing the coronal emission, line and continuum emission. This is a very famous flare observed in Proxima with XMM early on in the XMM mission, where you can see the X-ray light curve. It's very impulsive. When you're looking at the corona, you're looking at the timescales of plasma heating, since this is the hottest plasma that's produced during the flare. With the advent of Chandra and XMM, and I realize I'm just dating myself by saying that since they've been around for 25 years at this point, but you can look at density changes due to chromospheric evaporation, abundance changes. Looking at time-resolved spectroscopy, you can see the signal of dredging up of material from lower in the atmosphere during the flare. And in this particular example, Manuel Goodall found density enhancements in low temperature coronal plasma that were diagnosed by helium-like oxygen, which you can see here, and neon 9 as well. Okay, we do have the possibility to look for dynamics at X-ray wavelengths. This is a recent paper by Inoue et al. Looking at a blue shift of iron 25 seen during a large flare captured with the MAXI detector on the active binary IM peg. And the key figure is this one over here, where the maximum Doppler velocity was estimated to be about 2,200 kilometers per second by looking at the offset from where you expect the line to be and where it is. Okay, this plot I kind of is a in between flares and eruptions. There have been a couple of papers now looking at the dynamics during some flares, as seen in some of these very active stars. This particular paper by Chen reported the existence of cool and warm upflows in a flare on the M dwarf EV LAC. And this is a complicated plot, a complicated series of plots. There's an individual line in each column, and then each row shows you the top is the intensity of that line as a function of time. The bottom is this next panel is the velocity in a series of time bins. And then the bottom panel decomposes the line profile in each of those time bins. So you can see the Gaussians that were used to fit a stationary component and a moving component. So they examined a number of flares in EVLAC, and for one of these events, they found some shifts that appeared to be accompanied by a decrease in the coronal density, and they interpreted this as possibly being due to an eruption. There were other examples where there was no accompanying coronal density decrease. And so there they were modeling it as chromospheric evaporation. Okay. Other evidence for eruptions in the EUV and X-ray. This was a paper reported by Sophia Moscou in 2017, based on earlier data that was presented in Favada and Schmidt, a very large flare observed on the active binary system Algol. And what was particularly notable about this event is that there was a very sudden increase and then systematic decrease in the column density of hydrogen during the decay phase of the flare. That was published in the original paper. And then the later paper came up with a geometric interpretation of this as a self-similar expansion of a constant velocity ejecta as some kind of CME is moving outward from the star. And they noted that the time dependence of this is almost t to the -2, which is consistent with that self-similar velocity, constant velocity self-similar expansion. We already heard about some of Astrid Baroning's dimming results, and I think we even saw this particular plot. So Alina and I were on the same wavelength, so to speak. So here, the idea is that after some of these flares, if you see that the post-flare emission level is not the same as the pre-flare emission level, that mass has basically been lost. So it's this mass loss dimming as opposed to absorption dimming of the NH and the radio that I showed you before. Right. So that was a very quick summary through the electromagnetic spectrum. Some of the different things that you can use, that you can diagnose by doing observations in those wavelength regions. So now let's go to the second part and think about what kind of strategy we want to use to do a multi-wavelength campaign. There's a couple different ones, not just pick a star and stare at it. There've been a couple more creative ways to think about this. So, of course, the first one is pick a star and stare at it and get all the telescopes that you want or that you're interested. And I'm showing some recent results here. The figure on the left is from Ward Howard, following up those serendipitous ALMA flares with a campaign to try to understand the multi-wavelength context for those flares. This is millimeter X-ray and optical flares on Proxima. These are tiny little flares on a tiny little star, was essentially the title of the paper. So there is an X-ray response, there's an optical response, but the millimeter response is just whopping huge. It's 100 times higher than what you would expect for an analog on the sun. And these millimeter flares are only lasting for a few seconds, whereas the X-ray flare and the optical flares are lasting much longer. Similarly, Isaiah Tristan published a paper on UV optical and X-ray flares on AUMIC. This is a plot from that paper, and I'll note that there's radio flares being added. They found a number of different relationships between the X-ray, the UV, and the optical, which they interpreted as Newport events, where you have a characteristic relationship that you expect between the accelerated particles and the plasma heating that's happening as a result of the energy deposition of those energetic particles, things that are quasi-Newport and then non-Newport. And in true astronomer fashion, there's a type 1 and a type 2. So interpretation still TBD, but clearly there's complexities to the kinds of observations that we're seeing, kinds of flare responses that we're seeing. Similarly, Rishi Patel also did a point, pick your star and arrange multi-wavelength observations. These were TESS and SWIFT UV optical telescope plus X-ray in preparation, measurements of flares on a variety of M dwarfs. You can see some examples here of a nice white light flare and a UV flare. However, there's also examples of nice UV flares lacking white light counterparts. And they found only 27% of the NUV flares had optical counterparts, which was pretty surprising. It's still trying to understand why that might happen. Okay, so that was strategy A. That was what everyone thought we were just going to talk about. But let's talk about a couple different strategies. You can also plan a campaign targeting multiple objects. So instead of just picking one active star and staring at it and hoping that it will flare, you can use the fact that young stars tend to show enhanced magnetic activity and look at a field that has a lot of young stars in it. Jan Forbrich did this in the Orion Nebula cluster, finding extreme radio variability for some of these stars that were observed with both Chandra and the Jansky VLA. Guarcello reported on large flares seen in the X-ray and white light with XMM and K2. This is just showing you that field of use. You can see all those flares. The green ones have nice big flares, and then the panels to the right show the light curves. All right. Strategy C is to use serendipitously overlapping time domain surveys. So Clara Bressour did this by utilizing the fact that Kepler, during its main mission, also had observations with Galax. The same field was observed with Galax. She found over 1,500 NUV flares that did not have any white light counterparts in mostly G stars. And I need to speed up a little bit, but I don't have that many slides left. So another example of serendipitously overlapping time domain surveys, cosmology telescopes. The Atacama Compact Telescope and the South Pole Telescope are finding that millimeter transients are dominated by magnetically active stars in the solar neighborhood. And in this paper, they actually had some serendipitous overlap between TESS observations and assassin observations. Okay, and then finally, strategy D is to use triggered events. The SWIFT telescope, it was designed to study gamma ray bursts. It has seen large stellar flares in the solar neighborhood, and there's a whole network of ground-based telescopes that's set up to respond to these very interesting gamma ray bursts. And occasionally, when one of these stellar flares happens, they observe, and then they realize that it's not a gamma ray burst and they stop observing. But for this case on EV-LAC, there was an observation with the Liverpool telescope, only one observation, but it was very important. And then this radio telescope responded after another trigger from SWIFT. Okay. So that was a fairly whirlwind tour. I didn't focus a lot on specific science questions, but I just thought I would put these up here about what questions do we still want to answer? What are the different atmospheric responses during flares? Can we have multiple signatures of mass ejections to better bolster those eruption claims? Looking at interrelationships between flares and CMEs, and then looking at systematic behaviors across mass, temperature, and age. And with that, I will stop. Sorry, run over.
So we have a 3 minutes for the question. And please ignore it. What do you think is the mechanism for that approximate millimeter flare that's so short?
Yeah, so the question is, what do I think is the mechanism for these very short and bright millimeter flares from Proxima? So I think we're looking at just individual loops that are having accelerated electrons and producing this response. So yeah. I would like to get funding to do more modeling of this, let me say.
Why not go for therapy and something that permanent rate? More than everything that show us that the maximum mistake is not maybe a practical.
Okay, so the question was, since CMEs tend to be shy, why not try to observe the coronal rain? So yeah, so I guess my general response would be, I think we need to observe lots of these events to try to disentangle what's happening. As we found earlier in the Splinter session, we don't expect that there will be a simple relationship between flares and CMEs. And so, if I had my druthers, I would take all the wavelengths. And try to get a large enough sample that we can start to tease apart some of these behaviors.
I do want to point out there's one piece of the electromagnetic spectrum very important for negative 4. Maybe have ability whether planets are habitable or not, hard to make. They have atmospheres which are driven by